So today we're going to carry on with differentiable functions, and our big focus is going to be the chain rule and trying to build this up for functions of multiple variables. So this is 5.4, or at least it's the beginning of 5.4. There's more in 5.4. Okay, so big picture, what do we want? We want a simple rule for differentiating complicated functions. So we want to differentiate functions of this form. So h of x is of the form f of g of x. Okay, where? So this is the type of function we've been talking about, right? It's a real valued function of points in Rn. But it's going to have this composite form where, all right, here's our points in Rn. That gets passed into another function that has vector valued output, so multiple components, which gets passed into another function that spits out scalar valued result. So what do we want to know? We want to know, well, two things. Is this function actually differentiable using what we said about differentiability last time, not just can we compute its partial derivatives, but does it sort of locally look like its linearization? So one, we want to know that, and then two, we want to know if it's differentiable, what are its partial derivatives? How can we compute those easily? So I'm going to write the theorem down, and then we're going to spend some time trying to convince ourselves that this is true. So here's the theorem. Let's write this all down carefully. So let's suppose f takes inputs in Rn and spits out values in R, so spits out real numbers. All right, if we have any hope of building a chain rule here, obviously this function itself should be differentiable at the point that we're interested in. So we're going to say this is differentiable. Okay, at the point, why not? Okay, and then we're going to have our inner function. Our inner function is this vector valued object. So G is going to take values in Rn. Okay, so x is in Rn, so G is going to take values in Rn and spit out values in, sorry, let's do this the right way. Okay, so G and x don't have to have the same size, right? So this is the point. So f takes values in Rn, so that means G has to spit out values in Rn. So let's do this the right way. G is going to take something and spit out values in Rn. But what it takes in doesn't have to be the same size. What it takes in could be a different size, so we're going to call this Rm, and this, again, might be different. Okay, so what does that give us? That means the x's we're plugging in are in this space, Rm, which gets converted to Rn, which gets converted to an output that's R. Okay, so this also has to be differentiable at point x naught. Okay, and of course there's some relationship between this x naught and this y naught. They're not just random points. They're related because when we get put x naught in here, we want g of x naught to give us the thing that we're going to sub into f, which is y naught. So we'll say y naught is g of x naught. Okay, then this is going to be enough to guarantee that the composite function, this guy here, is actually differentiable, right, in the sense that we talked about last class, and we'll be able to get a formula for its derivatives. So then h is differentiable at x naught. Okay, and we can compute its partial derivatives. So the partial with respect to the jth component is, now what do we have to do? We're going to have to take the different partial derivatives of f with respect to all of these different inputs. So with respect to all of these y's. So df by dy. All right, evaluated at the point y naught. All right, and then derivative of the inner function. Well, the inner function is vector valued, so as we run through here, we're going to take the derivative of the ith component with respect to the variable we're interested in, so with respect to xj. Okay, so this, you've used the chain rule before, so try to write it out carefully, and we'll try to not get the n's and m's mixed up as we go along. But let's try to prove this. So, the big picture, what's the goal that we're trying to prove here? Yes?
The limit of the h of x minus h of x0 minus the sum of the partial.
Exactly. So we have this big picture, we're trying to prove h is differentiable. All right, and we have some candidates for the partial derivatives. That means that there's a particular limit that we have to evaluate, and we have to show that that limit equals 0. That's what it means for a function to be differentiable in higher dimensions. Okay, so we know what we're working towards. At the end of the day, I'm going to write down this limit, and I'm going to try to argue that this limit is equal to 0. Okay, to get there, presumably we're going to have to put it in terms of some information that we know. The information we know is that this guy is differentiable and all the different components of this guy are differentiable. Again, we know what that means. We know that that means there's particular limits that are equal to 0. So let's start by writing down the things that we know. Okay, so since f is differentiable at x naught, sorry, at y naught, let's do this. Let's identify, well, let me start by writing this down. So I'm going to write down the object that we're taking the limit of. Let's give it a name, because then every time we need it, we don't have to write down the full big beast. So let's write down this object. F of y minus f of y naught minus, we have to sum over all of these partial derivatives. F by dy evaluated at y naught. And then times the ith component of y minus the ith component of y naught. All of this divided by the size of y minus y naught. This is well defined everywhere, as long as I'm not dividing through by 0. If I wanted to, so this works as long as this is the case. If I wanted to define it at y naught, what would be a natural way to extend this at y naught? 0, exactly. So we know that although this is not defined at y0, it has a limit as we approach y0, right? So we can do the usual thing that we do. We have a removable singularity here, and we plug the hole with 0. And now, what can I say about this function? This is a continuous function. We've removed this discontinuity. So e of y is continuous at y0, since we know that okay, I can do the same thing with my function g. My function g is differentiable, so we're going to be able to write down an object like that. Again, I'm going to give it a name. There's going to be one for each of these components, right? So when we did differentiability, we were talking about scalar valued functions. This is a vector valued function, so I'm going to just ask that every component of it is a function, which I'm going to ask is differentiable. Okay, so since each gi is differentiable, okay, we can define these guys. I'll call it R. Okay, and now we do the same thing. So gi of x minus gi of x0 minus. All right, now I have to sum through all the partial derivatives. Okay, this is a function of x, which lives in Rm. So there's m things to sum through now. So the partial of gi with respect to xj at x0 times xj minus x0j divided by the size of x minus x0. Okay, and once again, we can plug the hole. We know that these guys are differentiable. That means this thing limits to 0. Okay, so now I've got these nice clean functions that are continuous, and I can plug whatever I want into them. And in particular, we know that they're going to hit the value 0 at the points we care about. Okay, and this is true since, again, the limit as x goes to x0 of Ri of x equals 0. Since that's true, Ri is also continuous. Okay, so these are the things we know. Now let's start trying to manipulate the thing we wanted. I don't really have anything else to do with this information at this point. So we want, I'm going to again give it a name, just for the sake of not having to continually write things out. We would like to work with this object. So I'm going to write down the same kind of ratio here, but now I'm doing this for my function h. H of x minus h of x0 minus, all right, h is a function of x, which lives in Rm. So we're going to sum over m objects here. So the partial of h with respect to xj times xj minus x0j over the length of x minus x0. This is the guy we need to take a limit of. And more than that, we're hoping to take a limit where when we plug these in here, we're hoping to substitute in these particular values for our partials of h. And if we can make this limit go to 0 with these values of the partial derivatives, then we will have shown differentiability. Okay, so let's see what we really want to do. Let's let's get rid of the h's here and put this in terms of the things that we actually know stuff about, which are f's and g's. F of g of x minus f of g of x naught minus the sum. All right, h derivative with respect to xj. We're going to have another sum pop up here. So I equals 1 to n. Okay, df by dyi evaluated at y naught, which is also g of x naught, times dgi by dxj at x naught times xj minus x naught j. Okay, so we have this kind of messy looking object, and we need to try to take a limit of this. At this point, I wrote down the thing I want to take a limit of. Now I need to substitute in somehow some of the information we already have. So what I want to do is look through here and see if I can identify things that look like either R or E. Yes?
You wrote this second sum there. Did we get that from somewhere, or are we just taking that from the
So this sum here, the sum of all of these things?
Yeah.
Yeah, so I got that from here. So we're hypothesizing right now that this is the value of our partial derivatives. If we can force this limit to be equal to 0, that would verify that actually these are the partial derivatives. Because that's the definition of differentiability, is that this limit can be made to go to 0 with some number here, and that number is identified as the partial derivatives. All right, so let's see what we can find here. So we've got, it doesn't matter what order I do this sum in, right? They're finite sums, so I can swap the order of the sums. That's not a problem. So let's see what we feel like we can work with here. I've got something like this showing up in the sum. If I switch the order of these sums, right? I have these di by dxj times xj minus x naught j. And this term doesn't depend on j at all. This term only depends on I. So I could pick up this sigma here, this j equals 1 to m sum. I could pick it up, and I could carry it over into here, right? And I wouldn't have left anything important out, right? Because these guys don't only depend on I, so I can pull them outside of the j sum. So let me explicitly write that, just because otherwise we're going to forget where that came from. So f of g of x minus f of g of x naught minus, I said I'm going to swap the order of the sums. I equals 1 to n. Pull out things that don't depend on j. So df by dyi at g of x naught. And then an inner sum, j equals 1 to m. And now I've got to write everything else out. So that's dgi by dxj times xj minus x naught j. All right, and why did I do that? I did that because this object right here, I'm trying to simplify. I want to simplify and get this in terms of things that I can easily take limits of. Things that I can easily take limits of are E and R. Okay, so this guy right here looks an awful lot like this guy right here. Okay, so what am I going to do? I'm going to rearrange this equation here to solve for this sum. So this sum is going to be equal to, if I move it to the other side, it's going to be equal to g of I minus g of j of x naught minus r times the size of x minus x naught. Okay, so that's all I'm doing here. I'm taking this, I'm rearranging it to solve for this term here. And you'll see that the rearrangement, right? This guy here, as it stands, is not defined for x equals x naught, but the rearrangement will be because I'm going to, it'll reduce to 0 equals 0 when x equals x naught. Okay, so let's put that in here. F of g of x minus f of g of x naught minus the sum from 1 to n. This part stays the same. Okay, so what did I say I have? I have gi of x minus gi of x naught, and then minus ri of x times the size of x minus x naught. Are we happy with that simplification? So I stuck an r in here. That's good. I should stick an r in here because that's a thing I know how to take limits of. I should be able to use that information somewhere. Now we need to figure out how to stick an e in here. If you stare at this for a second, at this part here, forget about the r. If you stare at this right here and you say, well, what if we identify g with y? G is our standing in for our y variable. Well, all of a sudden, that starts to look an awful lot like what we have right here, right? Derivative of f with respect to yi evaluated at y naught, which we identified as g of x naught. And then, all right, yi minus yi naught, right? So this is exactly the thing that's going to show up in this expression. So I'm going to play the same game a second time and say, let us isolate this and get it in terms of e of y in exactly the same way that we just did. Okay, so let's see. We're going to have an f of g minus f of g of x naught. Actually, we've got some of these terms here already. So not only do I have this derivative, you'll notice I have f of y minus f of y naught here as well. So I actually have all of this numerator sitting here. All right, all of that numerator is going to be equal to e times y minus y naught. So all of this is going to simplify right down to e of g of x times the size of y minus y naught, which is here g of x minus g of x naught. And then what's left? What's left is this term that involves the ri. So we sum from 1 to n df by dyi, evaluated at g of x naught, times ri of x times the size of x minus x naught, all divided by the size of x minus x naught. This, I hope, is starting to look like a little bit friendlier of an expression than we started with, right? Because we know a lot about what e does. G of x minus g of x naught divided by x minus x naught in magnitude. That seems like a friendly object, right? It has the feel almost of a derivative. Right? It's not exactly a derivative, but it feels like one. And that means hopefully we can somehow bound this object in terms of derivatives because we know this function is differentiable. Here, this x minus x naught is going to cancel with this. Ri, we know, goes to 0, so that's a friendly object. So let me just break this up into the pieces that I want to handle individually. This guy I like. G of x minus g of x naught over x minus x naught right? And keeping in mind, g is vector valued, right? So this is a length of a vector. It's not just an absolute value. Okay, and then plus all of this. And now I need to take a limit of this. The whole goal that we had was to write down this object, take a limit as x goes to x naught, and we hope that that limit comes out to 0. So now I'm going to do this term by term and try to show that all of these terms behave themselves in such a way that we should get 0 in the limit. All right, so first term is e of g of x. What do we know about the limit of this as x goes to x naught? 0. Why is it 0? Right. So we wrote down this function e of y, and we said it's continuous and it limits to 0. That says y goes to y naught. Now, we're not sticking just a variable, continuous variable y in here. We're sticking a function in here. So there's a little more that matters here. It matters also that g is continuous. Is g continuous? It is, because it's differentiable. And thankfully, we define differentiability in such a way that it gives us continuity, right? So if you were just trying to willy-nilly do partial derivatives with things where the partial derivatives exist, but you don't have this definition of differentiability where we're well approximated by the tangent plane, your chain rule could break down here, right? Because you're not guaranteed continuity. So this definition mattered, and this is the first place where we're going to see that this was probably a really good idea. Okay, so we know that E is continuous. E of y is, let me write this better. E of y is continuous. Okay, and we're given that g is differentiable, which means it's also continuous. Okay, and those two pieces of information mean that we can take the limit and get 0. Okay, so that's good. So this guy goes to 0. So now the only thing we really need to be worried about here is that this guy stays bounded, right? This does not need to limit to 0. It just has to stay finite. If I have something that limits to something finite, or even if it doesn't have a limit, it just has to stay bounded. Bounded times something goes to 0 is 0. So let's worry about this guy. Okay, so let's take him one component at a time, because again, g is a vector valued object. So I have something like this, gi of x minus gi of x naught divided by the size of x minus x naught. Let's go back to all the pieces of information we have. I mean, we think that in order to bound this, it matters that g is differentiable, because this feels like a derivative. So here's the part where we wrote down g is differentiable, and all right, indeed, something like this ratio appears in here. So same game that we've been playing so far is let's just rearrange this to solve for the piece that I need. Okay, so I'm going to solve for the piece that I need, and I'm going to get that that is equal to Ri of x plus the sum of these partial derivatives divided by the size of x minus x naught. Now, Again, I really don't care what this limits to. All I need is to show that it's bounded. I don't need a good bound even. I just need a bound. Any bound will do. So I'm just going to do all the crudest estimates I can think of just to show that this stays finite. That's all I care about. Okay, so this is going to be, if we do our triangle inequality, the numerator, I'm going to bound by the biggest possible partial derivative. All these partial derivatives exist, right? So dgi by dxj, these are just numbers, right? They're a choice of m different numbers. They're just finite. So the maximum is certainly finite. So I'm going to call this maximum m. This is the component-wise difference between x and x naught, is going to be bounded by the length of the vector. And then the length of the vector is here again. And we've done this, I guess, little m times. So I should include that we've done this little m times. Right? So I've given each of these terms the same bound. This is bounded by m times x minus x naught, and then we add them all up. Okay, where capital M is going to be equal to the biggest possible partial derivative we get. Okay, again, it's not that I'm taking the partial derivatives as a function and trying to maximize it, which is maybe a dangerous thing to do because we don't always have maxima. I'm taking the partial derivatives only at this particular point x naught, right? So this is just maximum of a finite number of values. So there's no issue with writing that down. And I'll throw all the i's and j's in here so that kind of get the same bound no matter what I put here. Because again, I don't care about a good bound. I just need a bound. Okay, so with this, if we simplify a little bit, we get a bound like this. So this certainly stays finite. Does this guy stay finite? It goes to 0, right? This limits to 0 as x goes to x naught. So what does that mean? That means that pick any epsilon you like. I can find a neighborhood. I can find a ball around x naught such that this function stays less than epsilon. Okay? And we're taking limits. We really only care what happens near x naught. Okay, so we can certainly say that this is bounded in a neighborhood of x naught. Since we know that this Ri goes to 0. Okay, so again, G was a vector valued object. Every component of this stays bounded. So the actual thing that we have is G of x, the length of all of this. Okay, so if I write out the length of all of this, this is the sum over all the i's. Okay, of gix minus gix naught squared. And I'll bring in this x minus x naught into here. Okay, so what are we doing? We're summing up the squares of all of these. Each of them stays bounded. So what we just saw is that each of these stays bounded by Ri plus big M little m and again, this is going to stay bounded. So this is bounded in a neighborhood of x naught. Okay, so this term goes to 0. This is bounded, so this product goes to 0. What about this term here? What do we need to do with this one? Nothing, yeah, we're done, right? So these are just numbers, right? The f is differentiable, the partial derivatives exist. We're only looking at the partial derivatives at one particular place. So these are just some finite numbers. Ri, we know, limits to 0. So we'll say we know that all of these guys are some real numbers, and we know that R limits to 0. Okay, so we can come back and conclude here then that all of this in the limit is going to go to 0. So we wrote down the thing that we wanted. The left-hand side is erased now. I think I called it Q. Q is bounded by something that goes to 0. Okay, so we can conclude, great. Therefore, the limit as x goes to x naught of this Q equals 0. And that is precisely the definition of differentiability. In this, again, in this careful form where we're not just computing partial derivatives, which is how we would have proved the chain rule last semester in R, we're doing this careful thing where we look at the linearization and make sure that that is staying close to our function. So we say, therefore, H is differentiable at x naught. And we've verified the values of the partial derivative because they are the coefficients that showed up in our linearization. Questions on the result, the proof?
Bit of a monster.
It's a bit of a monster, but I mean, I hope that each step by step, I didn't do any magic here, right? Although it was a bit long, I mean, my biggest concern here is that I'm almost guaranteed to mix up the n's and the m's at some point in time doing something like this, and I don't think we did too badly actually on that. So there's a lot of careful bookkeeping. This is the kind of monster proof where you have to do careful bookkeeping. There wasn't anywhere where I had to have a really big key idea, an insight to say how to proceed, right? You know, when we did Heine-Borel say, there we needed a little bit more insight into the direction to proceed. Here, I think it was more, I hate to use the word obvious, but it was fairly clear how to proceed, right? We wrote down the things that we knew using what the words mean, and then we simplified carefully, trying very hard not to swap n's for m's. You know, when we had those RIs that we were trying to rearrange for the piece we want, it's easy to make silly mistakes there, but it's the algebra that's the hard part. And you never have to do it again, because now you know the chain rule works, right? So that's always our hope for the monster proofs, is that they're monsters, but we do them once, and then hopefully they save us a lot of effort in the future. Okay, so let's play with it a little bit. All right, I'll do an easy calculus 3 type example and then a slightly more interesting and useful example. So just to let us take a breath a little bit, let's define some of these functions. Okay, y1 squared sine of y2 plus y2, y3. G of x1, x2. So remember, this is a vector-valued object. And it better give us 3 outputs, because I need 3 outputs to put into here. So x1, x2, x1 squared plus x2 squared, 2x1 plus x2. And then we define the composite function. Okay, so the composite function is going to be f evaluated at g1, g2, and g3. Right, and then you can start taking partial derivatives using the chain rule, and it's basically just a matter of bookkeeping at that point. Bookkeeping and using the rules we know about computing partial derivatives, which we just use the rules we know about computing ordinary derivatives essentially for that. Right, so if we wanted to do one of these, what would I have to do? I would have to run through these components. So df by dy1 times dg1 by dx1, because x1 is what I'm differentiating with respect to. And then I just run through the different components of f here. Always taking derivatives with respect to x1. Okay, and then again, it's just calculus. So we get 2y1 sine y2. Take the derivative of the first component, we get an x2. Partial with respect to y2 is going to be y1 squared cosine y2 plus y3. Derivative of the second component, 2x1. Derivative with respect to y3 is y2. And derivative of the third component is 2. Right, and then we remember, well, now I've got a mix of x's and y's through here. My function h is supposed to be a function of x's at the end of the day. So then I say, well, let's get rid of these y's. y1 is the first component of g. So 2x1, x2, there's another x2 here, times sine of y2, which is x1 squared plus x2 squared. Okay, plus 2x1 times y1 squared is x1 squared, x2 squared. Cosine y2 is the sum of the squares, plus y3, 2x1 plus x2, plus 2 times y2 is x1 squared plus x2 squared. Right, and these calculations, I mean, you've seen before. There's nothing magic or novel about them. And of course, you could alternatively plug your g's into here and take the partial derivatives directly, and hopefully you get the same result. You better get the same result. If you don't get the same result, the chain rule has failed, or you've failed to check the hypotheses of your chain rule, I guess is the other possibility. Maybe a more interesting result or example. This choice of g is not so interesting. You know, again, I could just plug it directly in there and be off. and running. More interesting would be to use this to do a change of coordinates, say from Cartesian coordinates to polar coordinates. So if you're trying to solve the heat equation or the wave equation in a domain with some kind of symmetry that makes polar coordinates really nice, then you might like to do a change of coordinates and write your P to E in polar coordinates. And the change of variables formula will help you do that then. Okay, so let's suppose that f of xy is differentiable, okay, on R2. Okay, and now I'm going to identify these variables, x and y, in terms of their polar coordinate representation. So x equals r cosine theta, y equals r sine theta. Okay, so this is my g. This is g1, this is g2. And they're certainly differentiable with respect to r and theta. No problem there. Okay, and then we're going to define h of r theta to be f of r cosine theta, r sine theta. Right, so h and f are the same function, right? If, say, this is meant to be the temperature in space and you draw your disk and look at the temperature, these will both give you the same results, but this you'll access by looking at the Cartesian coordinates, and this you'll access the result by looking at the polar coordinates, but it's the same function. Okay, so then we might want to say, well, how do I convert? What I'd like to convert, say, is the Laplacian. So fxx plus fyy would be great. So we start taking partial derivatives. So we say a chain rule applies here because this is differentiable, this is differentiable. So we can start doing the chain rule. Okay, dH by dr is going to be df by dx. So df by the first component times dx dr. Dx dr is cosine theta plus df dy times dy dr, which is sine theta, okay, and let's do dh d theta as well. Okay, dh d theta, so we're going to get df dx times dx d theta, that's minus r sine theta, plus df dy, r cosine theta, and that's our first partial derivative in polar coordinates. Now I'm rather more interested in going up to second partial derivatives because I would like to solve probably second order PDEs, something involving the Laplacian, for example. Okay, so I might not do all of these explicitly, but we'll do one or two. So we want d squared h by dr squared. Okay, so we need to take a partial derivative of this with respect to r. The thetas and the r's are independent of each other, so there's no derivatives to take there. Okay, so we're going to take the derivative of this with respect to r. That means taking the derivative of this with respect to x first of all. Okay, so d by dx of all of that plus df dy sine theta times derivative of x with respect to r, which is a cosine theta. Okay, and then the y derivative of all of this. Times the sine theta. I guess if I'm going to do this, the second derivatives of f should exist because they've popped up here. Okay, so where I assume that in order to do this, that f is C2. It has continuous second derivatives. All right, so let's see if we can simplify this a little bit. We get a cos squared theta times d squared f by dx squared. There's a cos theta sine theta here and a cos theta sine theta here, which I'd like to combine. These both involve mixed partial derivatives of f. This is d by dx, d by dy, and this is the other way around. So I guess, true or false, are they the same, those mixed partial derivatives?
They're the same.
They're the same. Why are they the same? Because we have continuous second partial derivatives, right? So we saw an example, right? The mixed partial derivatives, it matters in general what order you take the derivatives in. X then y is not the same as y then x. But here, I'm going to add this assumption that the partial derivatives are continuous and the second partial derivatives are continuous. That's a setting that allows us to just do them in any order we want. And that would be a typical assumption you might want to make on a PDE. Not always. We do second order PDEs where the second derivatives don't exist, but that's not for today. So let's combine them. 2 sine theta cos theta, and then we'll have this mixed partial derivative, which again is allowed because these things are continuous. And then a sine squared theta d squared f by dy squared. Okay, that calculation's okay? You can do these calculations? Yeah, so let me give you some results then. So we've got the mixed partial, right, which we would get by taking the theta derivative of dh dr. Right, which I won't go through all the details, right, but it would be our usual change of variables formula. So d by dx of this times dx d theta plus d by dy of it times dy d theta. And at the end of the day, that is going to be minus sine theta df dx plus cos theta d squared f by dx squared minus r sine theta plus the mixed partial r cosine theta plus cosine theta df dy plus sine theta d squared f by dx dy minus r sine theta. Okay, so some long expression, but you can work out what it is. I don't care if you copy this accurately or not. You can look it up afterwards. it's not important to have this memorized, right? It's important to know how to compute something like this. All right, and then there was one other second partial, which I am going to write down the answer but not the calculation, because the answer is going to be interesting. So we need to take the second partial of this with respect to theta, two derivatives with respect to theta. So d squared h by d theta squared is going to, at the end of the day, become minus r cosine theta df dx plus sine theta df dy plus r squared sine squared theta d squared f by dx squared minus 2 sine theta cos theta times the mixed derivative plus cosine squared theta times the second partial with respect to y. Now, so I have all these individual partial derivatives with respect to thetas on r's, but let's say I don't really care about any of these particular values. I don't care what dh theta is. I don't care what d squared h dr squared is. What I care about is what is the Laplacian. I care about the particular combination of these that gives me the Laplacian, because that's going to show up in all our favorite core linear partial differential equations. So what I want to extract is really, here are the terms that I want: second derivative with respect to x plus second derivative with respect to y. So we're going to stare at this expression for a second, and let's see what we see here. This term here, we've seen one other time. Cos theta df dx, sine theta df dy, that's actually written over here. So that's dh by dr. So I could simplify that to dh dr. Now, again, what I really want is the sum of this and this. Right now, they're multiplied by these sine squared and cosine squared. I just want ones in front of them. Easiest way I could think of to put ones in front of them is to say this is 1 minus cosine squared, and this is 1 minus sine squared. So let me break it up a little bit that way. 1 minus cos squared d squared f by dx squared minus 2 sine theta cos theta times the mixed partial plus 1 minus sine squared. And now a couple useful things have happened. So I've got the Laplacian here with some extra terms that involve all the second derivatives. So what I'm going to want to do is take these terms to one side of the equation, take everything else to the other. You're pointing to another part of the board, because you've just noticed that although there's a mess left over, it's a mess that we've seen before. And that's why I wanted to write some of this out explicitly. So what do I have here? With a negative in front of it, I have a cos squared theta d squared f by dx squared. All right. Sine squared theta d squared f by y squared. And the mixed derivative times this mixed partial. Sorry, the mixed term, mixed sine cosine term times this mixed partial. And this is going to look an awful lot like, so let's take the part I care about. Okay, and the rest of this is going to look like another one of my partial derivatives. So this is going to look an awful lot like, where'd it go? Like this guy right here. So now I should be in business. So what is my left-hand side? My left-hand side is this thing. My right-hand side involves a term that I care about. So I'm going to keep this guy on the right-hand side, divide through by r squared, move everything else over. And all of a sudden I have an expression for my Laplacian. Okay, so my Laplacian of f, which in 2D is this guy, equals, all right, 1 over r squared times d squared h by d theta squared. All right, move this guy over, divide by r squared, d squared h by dr squared. And move this guy over and divide by r squared. And I get 1 over r dh dr. Right, and the key is that this now lets us write Laplace's equation, the heat equation, the wave equation, all of these in polar coordinates, which could be a really good thing to do if you have some type of symmetry where polar coordinates makes life a lot easier than Cartesian coordinates. Okay, and it's not just as simple, the Laplacian in polar coordinates isn't just as simple as summing up the second partial derivatives, right? You have to do the change of variables carefully, but now we see that actually there is a simple expression for that. Although there were a lot of ugly details along the way in the individual derivatives, things simplify down pretty nicely. And now we can write many of our favorite PDEs in polar coordinates. And of course, you could do this for other differential operators too. Questions? What else can we do with differentiable functions? We can have a mean value theorem. That was something that we liked a lot in 1D, and it makes sense to try to extend something like this. So mean value theorem. So let's suppose that f is continuous at 2 points in Rn. Now, what's going to happen with the mean value theorem? We have 2 points that live in space, and we're going to somehow relate them to something that happens in between. So what we're really going to be doing is restricting our attention to this line segment that connects them. And the line segment is, of course, embedded in higher dimensions, but it turns into just about a one-dimensional problem. So we're going to say that f is continuous at these points and differentiable, okay, on the line segment. Connecting them. Of course, differentiability everywhere will work, but this is actually the only places where we'll really need it. Then we're going to, it's not going to be quite as simple as our, we make it look like a derivative, rise over run, because we've got multiple components to keep track of. But we're going to be able to say that f of x2 minus f of x1 is equal to, and now we have to run through all these different components that we have, right? We don't just have a derivative, we have all these partial derivatives. Is going to be the derivative with respect to xi, evaluated somewhere, okay, times component-wise, x2i minus x1i. Sorry, 1i. Okay, for some x naught on the line segment. Okay, so let's try to prove this. Again, this feels one-dimensional. So here's my x1. Here's my x2. I'm going to call this line segment L. Okay, so L, the line segment, is going to be the set of points in R2. Living on this line segment. So I'm going to make this feel one-dimensional. We've talked about writing lines in parametric form. Okay, so I'm going to introduce a parameter t that tells me how far along this line segment I've gone. It's our usual way of parameterizing a line, except t isn't going to be all real numbers. T is just going to take on a finite range of values that will get us from here to here. So it'll be x of the form x1 plus, let me write this in a consistent way, t times x2 plus 1 minus t times x1. Okay, where t is between 0 and 1. All right, so t equals 0 means I'm at x1. T equals 1 means I've traveled to x2. So this x here, this is really a vector-valued function of one variable. Okay, so I take t, my one variable, as an input. It spits out this vector-valued function that lives in Rn. This can be Rn. It doesn't have to be R2. So I'm going to try to write this in terms of a function of one variable, but we'll see our chain rule is going to pop up here with this guy here sitting in place of our g. Okay, so let's write h of t equals f of x of t. Okay, so what have I done? I've just taken the function I started with and restricted it to this one-dimensional domain. Okay, now let's see what we can do. This is a function of one variable. So it would be natural to say I already have a mean value theorem for a function of one variable. So let's use it. So the mean value theorem for functions on R let's see, what do I need? I need h to be continuous and differentiable. So let's see. We're given that f is continuous all the way on this line segment, right? It's differentiable everywhere between here, which means it's also continuous all the way between there. Okay? We just showed that if this is differentiable and this is differentiable, the composite is differentiable. Well, x is the nicest function you could just about hope for, so certainly differentiable. Okay, so we know that h is certainly continuous on 0, 1 and differentiable in between. Okay, and this follows from our chain rule. Not the 1D chain rule, the full version that we just proved, because this inner function is not a one-dimensional object. Okay, and that means I can call on the mean value theorem here. So I can say, well, by the mean value theorem, there exists some t naught lying between 0 and 1. such that the derivative here is equal to h of 1 minus h of 0 divided by 1 minus 0. Well, h of 1, x of 1 is x1, right? So we can get these values in terms of my f. And then what do I need to do? I need to use the chain rule to get this derivative also in terms of derivatives of f. Okay, so let's do it. We know that, all right, h of 1 minus h of 0 is equal to f of x2 minus f of x1. Okay, we can take the derivative of this with respect to the chain rule. So by the chain rule, h prime of t naught is going to be equal to, well, we have to sum all of these over all of these different partial derivatives. So the derivative of f with respect to xi evaluated at x of t naught times the derivative of the inner function. So if I start taking derivatives of x with respect to t, well, again, x is a simple function. It's a linear function. So what do I get? I get x2 minus x1, which is a vector. And now I need to take the ith component of that vector here. All right, t naught lives somewhere in between 0 and 1. And that means that this function lives somewhere on this line segment. So we can put these all together, say this equals this, means that indeed f of x2 minus f of x1 is equal to, we sum over all of our partial derivatives. Okay, for some x naught on the line segment. So we've got our mean value theorem, which is really useful. It's also, first of all, are there any questions on this? You might remember that the mean value theorem, at least the one-dimensional version of it, was a special case of a bigger theorem. Do you remember what the bigger theorem was? Taylor's theorem, exactly. So this is, the mean value theorem is really a zeroth order Taylor theorem. Okay? So where I say, well, h at some point is equal to h at my reference point, and I'm going to stop there, and that means my error looks like the first derivative evaluated somewhere. This is a special case of Taylor's theorem. So we want to take this and push it up to create a Taylor's theorem now for functions of multiple variables. That's where we're going to be going from here. Taylor's theorem being one of my favorite theorems in applied math. I mean, I'm a finite different person, so like all I know how to do really is Taylor expand. That's my bread and butter. So we're going to get there next class. We're going to have to build up some notation for this because all of a sudden we're going to have a lot of different partial derivatives to keep track of at once. So we're going to spend a bunch of next class just building notation that will let us do this, and then we can use chain rule and compute this. Yeah?
So when we did the definition of the differentiation, but we wrote the function, but we linearize the function.
Yeah, when we linearize
that was the Taylor series, right? Expansion of the function.
So we didn't use Taylor's series to do that. We checked the limits directly. But yes, it's also a consequence or closely related to Taylor's theorem that somehow this looks like it's linearization. So yes. We didn't use Taylor's theorem because we didn't have it, but yes, they're extremely closely related. All right, I leave you there today.